Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have a practical lecture about MPI, and is basically based on our lecture 2 from the last time, where we had the conceptual ideas of MPIs, basically being the de facto standard in message exchanges in parallel computing. We talked about point-to-point communication, but also had this interesting collectives that we will also demonstrate today. But before we go into the demonstrations of all the different elements of MPI, let us review what we had the last time. This was basically the initial idea of thinking about how we going to involve different processors really in one application, right? So this is now the importance of parallel computing and parallel programming, if you want, across different processors. I have one application that then should do a certain element in this application in parallel. And in order to do that, we want to exchange data between the different processors to basically operate on different data elements, or basically to communicate the results of a time step. Maybe when you think about an application that goes beyond time, basically over certain time, and then we'll have something simulated, for instance. And if you remember the last time, we had one example that I want to basically bring here again. If you think about, here is one of the interesting aspects of a parallel application called glacier calving simulation, where first there's basically a mesh generated, and this is really serial that is not requiring lots of parallel processors or different cores. Instead, we generate the mesh, and then from there we have a solver that basically then computes different elements basically before really the glacier carving is happening. And then we basically have to transform this from one specific parallel application called ELMA to HIDEM. And in doing so is also possible in serial after this parallel run has finished. And once I have then this basically prepared, then the real calving can be computed. And we see that's much more, as you see also in the video here, that's actually what we mean with glacier calving, right? The real fracture. Then 560 cores are needed because it's much more computationally expensive. This is just one time step, more or less, if you want. Then we basically have to do this in a loop. And this is now the idea of many parallel applications, so that you basically have then the results essentially recomputed in another time step to update the mesh, then do the same runs again, of course, on different elements, basically of the data, the fracture and the calving over time. And we see this here iteratively will always look different. And that's why we have to update the mesh and always compute the calving in new. In order to then basically communicate the results of, let's say, one run part, or basically to communicate the different data elements of the mesh of this glacier calving, we need parallel computing in the terms of sending data from one processor to another. This is necessary because we talked about that MPI is essentially meaning distributed programming in terms of distributed memory. So the data that you have in one processor, you see that also here in one of these kind of processors, is here in the memory and should be going to another processor and has another part of the memory for its data element. So if you want to send the 17 here in the data element, you need to have a mechanism to really send it over so that the processor actually can maybe update its data item from 80 to 17. Involving just one processor and another one is called MPI point-to-point communication, which is basically more precisely illustrated here. Because what we also said is, if one processor wants to send something to another, that's fine, but the other processor needs to be ready to receive, right? So we prepare some system buffer so that the data has actually space in the other processor memory space, and that the processor is really ready to receive. And for every send you do, there will be a matching receive that we will also see then later in our MPI demonstrations. So by doing so, we had also the idea of this MPI com size and com rank, where we noticed when we do this and we work with this, every of these processors will actually execute the same application, right, with the same source code that you see here. So the way how you then differentiate is then that every instance basically from these processors get their own rank in a communicator. We learned already the MPI-com world is a world of all processors, which is always there. But we will also learn in later lectures how we can create subgroups and then basically work only with the communicator of this group. This could be useful, for instance, as we discussed with the boat. So there's basically one part of the communicators compute the physics maybe with the water and the waves, the wave propagation over a certain amount of time, while another region of communicators and processors will then basically deal with the boat movement on top of this water and the physics involved in this. Just as an example, which is very illustrative, obviously you have here the glacier calving as a quite cutting edge example. And if you want to know more, we have a publication on that here. Now, we basically also introduced something which was a little bit more involving a smart way of communicating not only to one processor at the same time, but to many processors at the same time. And this is called the MPI collective communication, which basically involve all the different processors in one communicator in order to do some smart communication. The smart communication can be manifold. We have learned that one item can be, for instance, distributed. You see here data is going to all the other processors in the communicator. That's what we call broadcast. Then we basically have said we can maybe scatter an array to say, well, here's an array of 3 elements, and we want to basically get this to all the other processors. You see one gets a 10, one gets a 20, one gets a 30. An operation called scatter, and the more or less inverse of this called gather that you basically have here is then the other way around. You would have prepared an array and you want to collect from all other processors then basically some data. And there was another very powerful operation which basically has many flavors, because you can basically change the idea of which operator you use. Here is an example of a global sum, which we have in the idea of doing an MPI reduce operation, which is called this way, but combining it with a certain operator called the plus. And there are different ways how you can implement this. Here you see now every data item 1780, they all will be automatically directly basically added to each other and then basically collected already or reduced, if you would say, on one processor. And there's all reduced, which then also brings then these results again to all other processors and so on. And this helps us enormously to save source code lines and the clarity of MPI programs, because you don't have to do 4 loops and send and receive to everyone in the communicator. Instead, you just use a broadcast, for instance. And I hope these mechanisms that we have dealt with in lecture 2 is really the idea. Coming now to lecture or practical lecture 2.1, where I demonstrate a lot of these things in practice, where this hopefully becomes more clear. Needless to say, in your assignment 1 that you will experiment this much more deeply on your own, and then hopefully have much more understanding once you have performed assignment 1. So what we will do today is really starting again with C-based MPI programs, a little bit more elaborate though, that we really include MPI. If you remember, the last demonstration were more or less simple C. Now we want to understand MPI, the parallel programming in it, the different ranks, what role they will play. And also with this, of course, the idea of this parallel environments, which we need with MPI Init and MPI Finalize. Then we had also this interesting PingPong application, interesting in one way because it's just point-to-point communication, but it communicates also the idea that when one is doing a ping to another processor, the other processor needs to be ready to receive this ping, right? And in order to do the pong back, you also need the other processor that initially was sending the ping to be ready to receive the pong. So the idea of the send and receive and being ready for it is one part of the first idea, including, of course, our little hello world MPI that we always need to start first with. And then a little bit of thinking about what is a job script context. Also, when you think on our U-turn system, what does it mean to allocate maybe just 2 cores or 2 nodes and so on. The second part then will be going more into deep ideas of the broadcast operation, And of course, we will review the collectives again, as I just did now. There we also have to understand a little bit the difference between the point-to-point communication and the collectives, the role of the communicators again. And then in the second half of the second part, we want to explore a little bit a concept called the wall time. It's a very practical concept, which means a scheduler will given some time to execute this job, and it's so-called maximum time. And when this, let's say, time is not enough to basically have your application executed, it will simply run against the wall, as we say. So it will actually cancel and stop. And we want to understand this with a couple of practical examples. And these all parts of the outline will be also part of assignment 1. So basically, practical lecture 2.1 is directly relevant for assignment 1 and helps you along the way. What it brings you is hopefully to really think again the idea of parallel programming, that it can be quite complex. It's not at all so simple as normal programming. And then also why we need different abstractions sometimes on various levels when we do parallel computing, right? We will see point-to-point communication is already very nice. Collective operation is very nice in a certain way of abstracting already from the network. All you need is basically to define either communicators or a specific rank you want to send to. All other parts, right? The TCP, IP, whatever you normally program in HTTP headers, it's not happening here. But basically, we also don't have to really go on the lowest level of the network protocols in order to send something. So this is quite a nice abstraction. And with this, you will be able, after this lecture already, to start engaging in scientific domain-specific applications, because you will see that many of these production applications that you see a little bit illustrated here, whether it's plasma physics, astrophysics, or earth sciences, whatever it is, usually many of those use the MPI collectives. Many of those still leverage MPI point-to-point communication. So you really are ready to program in HPC. And this is, of course, something what we also want to teach here. With MPI being the de facto standard, more or less, in parallel programming for distributed memory, we start with this. And this brings us back to programming and compiling, of course, C applications, which we will start with now. And reviewing a little bit what we had in lecture 2 all along the way, but this time, as I said to you also, we want to do this more practically. So let's go back to our basically idea of the cluster here. This is again our MobiX term. If you remember from our earlier ideas, we will log into Krafla as a first jump because I'm not in the university network here. This is an error you can basically ignore right now. This always can take a little bit of time, but don't worry. We can maybe spend this time reviewing again the idea now. What we will do now is the idea of MPI concepts. And when we start with the real basics, we will go to an application where we then, again, using the C compiler and then using a job script to inform basically the scheduler about a certain application. We will this time, let's say, add to the normal C program that we had already in one of the last practical lecture 1.1. Instead, basically, we will add some MPI header so that the MPI functions are known. We will have the parallel environment between MPI Init and MPI Finalize. So this is the area where really some parallelization can happen. And then we'll play a little bit with the idea of what means now com size and com rank in MPI. In the meantime, we're probably logged into Krafla. I will actually increase here the font size for the recording. Now we are in this Krafla, basically, and we have said we want to do now the idea of hopping to Uturn. Here you see now we can do this simply with SSH and then using our password. And finally, we are already on Uturn. So this is now, I think, getting more clear when you're doing your assignment as well, when you get all your logins and can access the system. I also talked to you earlier that it would be quite useful to create a hierarchy of basically directories. You see here in the 2023 course, it's something we're interested in. So let's look into this. But when we look into this with ls-l, you see already I created something called MPI. There will be another lecture series on OpenMP. That's why I also would recommend, if you play around with the assignment and so on, do something similar, create your directories. If you remember, you can always do this with the mkdir command in this mkdir Morris if you want. Then you have a directory Morris, and you can, change into this and do something with this, and put your codes really in a very specific directory. That's what I want. And you see here we have already done so for the others. Hello was already existing the last time. Let's look a little bit now into Hello MPI, which is now the substance of today. And everything which I will demonstrate is basically already also on the slide. So I will not go to every little slide because we also want to have some practical work here. We remove here, for instance, the executable hello, because this is also something we wanted to look in and see and review again how we do this. Here you see now the hello C, but this time we added this idea of the MPI function. So we need always the MPI init as we had in lecture 2, the MPI finalize. So this means between those we can do parallel computing. Now, of course, hello world is quite trivial. We also, by the way, have to include the MPI headers here to get the specific MPI operations that we can use for the compiler. And of course, here the hello world is now very simple. You say we will give out hello world, and this is what we have done before. But here it's now interesting for us to understand that every instance of this would have a certain rank, right? And this rank information is something I can put in the variable rank. And then the overall size, how many actually are in the communicator MPI.com world, are then put into the size. That's why there's this ampersand. So we will basically write into this the information given out from these two functions. When I have this, I can always see basically which rank is now executing this hello world, let's say, printout. Interestingly enough, you see also it's not created for 4 cores, for 12 cores, for 18 cores or so. It's basically independent, right? Independent of the number of instances you would create out of this. And now this is also something which often is in MPI programs. So let's look and review this a little bit. If you remember, we had always this module load GNU and then open MPI is one of the implementations of MPI that we're going to use. And then we have to compile this specific C program we just looked in. For convenience, I do something, this -o to get a bit more the overview here. And now we have our executable. Now we also learned the executable alone is now independent from the number of cores or processors or even nodes. So how we do this, you remember a little bit from the JavaScript idea. The JavaScript has here this parameter n. And the small n refers to the number of cores. A big N refers to the number of nodes. I will discuss and basically also later demonstrate this again. Important is that we have now 4. So we ask for 4 cores to the scheduler. And we have this particular executable that I just compiled, right? So we want to 4 times instantiate this, but instead of having 4 independent applications executed, we know that basically now with the rank and size information, we expect something that they will all know of each other. We don't do some communication yet. No ping-pong, we will do this in the next example. But what you basically should realize is that when we do this now, and you see here in the queue step, the job is already finished and completed. So there should be an outcome. So we would have basically very soon an outcome where we can look in that everybody is aware that there are actually 4 overall cores and every one instance of this application. It's the same source code, but basically the same source code executed in 4 instances will always have a unique identity, and this is in the rank. And that's how we can differentiate then between the different processors. Let's look how this works when we have the more SLURM outcome, right? And you see here very nicely, I am the first, the second, the third, and the 0 out of 4. 0, obviously in computer science, we always start with a 0 identity. What you also see is when I do this now a couple of times, it's the beauty of batch systems, right? I can do this, just repeat that. The only importance is that I have different job identities, right? This is the unique idea now of these jobs of this cluster that I execute on your turn. So that means, in other words, we get several outputs. But what you also should see that basically it's not always the same output. Here we had basically starting with 1, 2, 3, 0. If I now do basically a modification of this and go maybe to the next one, you see that suddenly starts with 3, 1, 2, 0. Or you can go on and go on, probably will find another one with 1. Here's this very beautiful 0, 1, 2, 3. It's not really deterministic. And this is because basically there's some certain race conditions on the output. So everybody is not doing the same, has a chance to really write in the output at the same time. And with this, basically this output can vary. Still, it's the same application executed, let's say, once, but everybody is aware still of the all for communicator. Now, when I do this S-pitch a couple of times, it is, of course, executed several times, but also only 4 cores per run. So it's not that now, because I executed here 4 times, we have 16 cores for this application. It's 4 times 4 cores. And all of those are basically inherently knowing of each other, but don't know anything about the other jobs that have been submitted. Right, and this was already a little bit the idea of showing you and demonstrating you this part. You have seen the size is quite nice. It comes out of the MPI.com world. When we create later our own communicators from different groups, we will see that even within this group, we will then assign new ranks to this. You see that here a little bit illustrated that we have rank 0 twice because they are in different groups. MPI.com world has just one rank 0, for instance. But this is something what we will learn later. And then you have basically seen that with Hello World, we can actually, when we add this, and this is all described here in the yellow blocks, I will not discuss this very long because it's more or less what I also demonstrate you. Important is here that the valid C program is also basically what we created here and added. Then here's nothing else than MPI yet. This comes with adding the MPI header and MPI Init and Finalize. Now we're starting really having a parallel MPI basic building blocks implemented. And then, as I said, the com size and com rank is probably the functions you always, together with Init and Finalize, find in almost all MPI applications, because basically this is always needed to find and understand the rank, because I want to work with it. I want to have a big problem crunched into smaller pieces and then solve this application in a collaborative way. And this collaboration includes message exchanges about data, includes working on different parts of the application, but with basically different data elements or different variables. So hence, what we miss here with the Hello MPI a little bit is now the message exchange. You would use MPI for message passing. That's why MPI stands for Message Passing Interface. Now, in the moment, we were basically not have sent any message. So we wanted to just understand that basically we have this rank information, which is very unique and very important. So basically thinking about that when we now have these different ranks, we want to solve a bigger problem. Let's say maybe here cluster these different data items with sort of a clustering algorithm, which we use maybe with MPI up to 512 cores. So basically you would crunch down this domain into smaller parts. And this is something what we also have the next time. When we talk about lecture 3, then I will talk more about domain decomposition, crunching a big problem into smaller pieces. But by doing so, we start a little bit now by the idea, then we have to communicate some of the results maybe from one space to another, from one processor to another, and that's where this MPI message exchange start. Hence, we will look a little bit on a very simple idea, basically just implementing ping and pong. So in order to do this, it's again important to understand what I had here summarized for you in the parallel practical application. We were aware of different ranks. And this helps us now, because if you think about that, you have the same application that you want to execute in parallel here, right? We have the serial part, and basically here also after the MPI, finalize or init MPI before here. When you now execute this, it's the same application, the same source code. How in the world we should know that one is doing a ping and one is doing a pong? In other words, who is doing the ping initially and the one is receiving the ping, and then performs the pong and the other is receiving the pong. So that's something now where we try to use this rank information in if statements and would basically, with this, have the chance that every application will have their own identity. And this becomes very handy if you have big applications. Here, obviously, the ping and pong application is a little bit, small, trivial, but it captures the essence of point-to-point communication. And on top of it, also really using the identity of this rank information, which we do also in very big applications. Again, we learned in the conceptual ideas, this is really important that we are then also ready to receive when I do a ping, right? So hence, we cannot just say, if I am processor 1, I send something, and then the other processor should send something to do the pong. So hence, this ping pong is a little bit loaded in the idea that we have to break it up and say ping is one completely message exchange that you see here, saying that one processor is basically performing the ping, but the other one is not directly doing the pong, but preparing to receive the ping from the processor 1. And then, of course, for the pong, everything is vice versa. Then the processor 1 needs to be ready to receive the pong. And this needs to be reflected in the source code. So let's look how that could work in the practicals when we now look again in these applications. So I think here we are finished in the Hello MPI. Let's move ahead to the PingPong. That is quite interesting here for us. We remove the slur, maybe remove the PingPong here. It's old. And look a little bit into the PingPong C application. And I will explain it a bit. Again, the slides will obviously have much more detailed information with yellow blocks. But it captures the way what we want to actually demonstrate here. Again, we include the headers here for MPI. That's important. We have the Init and the Finalize, also very important for us, as we already know. We have the com and rank information. You see, sometimes it's called size. Some people call it number of tasks. So obviously, that's just a variable that will be filled by this operation, so we can name it as we want. But I will still suggest to you, use the rank as the rank. And this really helps with clarity and readability of the application. Now, because we're starting the send and receive operation, we maybe want to obtain a certain status of this. In other words, do we really receive something? Right? So that is important for us to understand. Is there really something going over the wire, or do I just trick you and say, well, there's a send and receive operation here. There will be probably something going over the wire, but how we can test it, how we basically can demonstrate it, will be something in the status variable here that we declare here, and that will be filled by each of the receive operations, right? So then we can basically determine, do we really received something? And we use the status information then in a printout of understanding later what was really received. And in order to make it more interesting, we also want to know how much was basically going over the wire. So we do a count of the status, which basically says how many chars were going over the wire. Now, the out message is just X. So basically you see here a little bit that we only want to transfer actually one char. And this is also what we reflect now in the programming of it. Firstly, you see very clearly that we now differentiate between the identity of the processor that should initialize the ping, while the other one, the rank 1, when we ask for 2 processors, for instance, should do the pong later. But we also said, like, okay, if one processor is now doing a send with one char, which is this X, to the destination, which is rank 1, the other one, in this MPI.com world, then there needs to be this rank 1 ready to receive. Hence, we have in the else if rank 1 now basically the receive as the first operation, because when the ping is coming out, I want to receive the ping. And you see here, you have a buffer of this in message, what we basically also discussed the last time. It's not only that I basically have the data of the out going out, because also here with the in buffer of the message I'm ready to receive from the source, which is 0, and also in the same communicator. On top of it, I fill the status information. which MPI gives me of really understanding what's there really something going over the wire, right? This is so something which is interesting to us, and we will basically look into a little bit. Then obviously, when this is now ready, you will see this send will work. And here, basically, the source code in this two instances, in the one that is receiving, will stop here and just waits until really the send comes out, right? So basically, this will be initialized, and the send will basically block unless basically this other processor has received something. So once this is received, we see that the second processor now, after the ping is done, right? This is the ping. This is receiving the ping. And now I initialize the PONG. And of course, this is going vice versa to the basically destination, which is our rank 0 here, also 1 char. So the X is going back. But of course, here, in order to send the PONG and being successful in this, the first processor then has to be ready to receive the PONG. And this enables us now the simple application PingPong. We can see how much was going over the wire here with the MPI get count, and we'll just give that out in a small output here, how many basically were really going over the wire, and with the tags and the kind of idea which basically gives us then some proof, so to speak, that there was really something going over the wire. So again, let's maybe go back to the slides so that we don't lose the connection. Everything which I demonstrated and shown here is basically here. You see, it maybe makes sense to look in some of the MPI specification with examples to understand it more if you want. Also in the assignments, Dino MPI and the examples, they are sometimes very good and students like them. So this is something I would recommend you. All other things I basically have described to you. So let's come back to the practical idea of really getting it running. And another one is just maybe basically, I forgot to say, we don't really coded it for 2 processors, right? This is another element. Of course, here, more or less, it is coded in the sense that they're just doing 1 ping and pong. So 1 processors are basically needed here to do the application, a rank 0 and 1. But the actual number of processors, again, is important now to understand, is in the submit PingPong operation. So we ask for 2 processors only, which is in this application very obvious, right? And perhaps here we don't really need to have a big scalability. As usual, we have to, of course, compile it first. We say modulo GNU open MPI. Then we had our MPICC, if you remember, with the source code. For convenience, I name it PingPong. And as you know, in the job script, this should match, right? So the PingPong executable that you have here, and one way of finding that out is basically the following. You can do pwd, print working directory. So you see that this is now really the one we just compiled, the directory. And inside this directory, I have this PingPong executable now. So basically we have an MPI/PingPong and then /PingPong again to execute. And this is something which we should also see in the job script. So every now and then I see that students basically forget a little bit about this. So here you see MPI PingPong, which is a directory, but of course we want to execute with MPIRun an executable with MPI. So that is the other PingPong you see essentially here. But when you do this in the practicals in assignment 1, I think it becomes very clear, and the steps are almost always the same. Module load, MPICC, and then what do you expect? We SBatch it, right? And now basically execute it. It's a very tiny application. So also here we assume it will be very quickly, basically completed. The output usually takes always a little bit time. You see, it's not written yet. It's because the scheduler is now basically working on the output and provides us with this information. And this is what you see here now with the SLURM output. And you see here the ping received basically 1 char from task 1 with tag 1. So really the task 0 was getting the ping over to task 1. And you do see also the pong task 1 then basically gave the pong back to the task 0. So again, this will be also part of assignment 1 to try out, to work yourself. So with this, I think it will be clearly going very easy in your brain when you do it with your own examples. Towards the end of this first part, however, I wanted to touch back on one important part, which we left out a little bit in explanation. You see here this job script N2, which is of course a key in basically parallel application, the amount of cores, the amount of nodes, and there's actually much more fine-grained ways, threads you can do in some of the batch scripts and so on. Here we stick to capital N and small n, which means the number of nodes or the number of cores. And this is something I want to demonstrate you to understand that a little bit better also when we come to the final step of this. So we can reuse here PingPong for convenience, but we'll maybe quickly go back to UTUN to understand a couple of things. So here you have the UTUN system of our competence center, EHPC in Iceland. And this is this UTUN cluster. We learned there are 4 nodes, right? And each of them has 12 cores. So let's look at the usage statistics, where we said, you see also there's actually more happening now on these different systems. And we discussed the last time that UTUN essentially itself is just the login node, because we have this concept of compute nodes that you see here with 0, with 2, 0, 2, 1, 2, 2, 2, 3, and UTUN, right, which is now important, the login node. You see also, obviously, I seem to have computed a little bit here. So you see already a little bit of load on compute 0.2, which basically is one of the nodes we have. And inside these nodes, of course, you have different cores, which we explained, this 12 cores, for instance. Hence, we would now expect when we do, let's say, 2 cores, that this is enough to be executed on one compute node, maybe compute node 2.0. But how we can see this, how we can check this, this is something where there's an interesting command, which you can use for several different elements like scontrol show job ID. And you want to do some output there where you can use the job ID and to get much more, let's say, verbose information about the job. So this is basically more than just the output. You see, this is all information we can get under this specific job ID, which is unique. And we learned, I asked for actually in the job script 2 cores. Right now, when we look at this, we see there's a node list saying compute 2.0. We have a batch host 2.0. Number of nodes is obviously just 1 because 2 cores fit in 1 node. We have 12 cores per node in UTUN. So let's say when I just have 2, it's enough to have 1 node. So and you basically see that again here. You see the compute 2.0 is here basically given again as one of the nodes. So what could we do to change this? Let's say, assuming that we want to ask for 2 nodes, which apparently, of course, in this trivial application is not really needed, right? But for the sake of demonstrations, let's see what's happened when we do -n capital 2. So this has a complete different meaning, although the application will still basically be executed and will basically realize with 2 cores communicating. But now we ask for 2 complete nodes. Hence, basically what you not should do is doing exactly what I just did now, right? This is just for demo purposes because here you block a complete node, 2 nodes actually, right? So here's just the idea of let's submit this to understand a little bit what these parameters are doing and how we then, of course, normally can also actually scale quite higher by, just executing this on different nodes. And consider one of the production systems in Jülich Supercomputing Center I was showing sometimes. This is, of course, then having very many nodes available. And with this, we can scale up very highly. Now, basically, we see also the output has been written. And apparently, as we see already from the size, as an indicator, there are not big surprises. It's exactly the same output. That's what we assumed. There's a ping and, of course, a pong. But what should be different is now when we do, again, our scontrol and show the job ID with some outputs about particular this one, right? Then the other job we now submitted, because here in the job script, we asked for 2 nodes. And this should now be reflected in this detailed information somewhere, which you see, for instance, here already. The node list involved in this job was 2.0 and 2.1. right? So this is what these brackets mean. We didn't have that when we looked here, right? There was just 2, 0. Now, obviously, I asked for 2 nodes and got 2 nodes, which is also reflected in this particular output. Number of nodes are 2. Still, the number of CPUs involved have been just 2, right? We had to send and receive, and basically a rank 0 and rank 1 exchanging information. But the real number of nodes was 2, and I occupied more or less basically these 2 compute nodes, which is nothing else than you see a little bit here, compute 2.0 and compute 2.1. Now the load is basically, let's say, so little that it doesn't make a big difference here. For that, we maybe should do here and there sleep later, what we do also in the second part of the lecture to understand a bit more. I summarized this information, of course, also for you here a little bit on this slides. And I think that's all what we can do for the first part. And we continue in 10 minutes for the second part, learning more about MPI collectives.